Organic Chemistry Part 2. Topics for today: alkenes and alkynes, optical isomers, aromatic hydrocarbons. Starting with the alkenes, they have a general formula CnH2n, where N is 2, 3, or other small whole numbers. You have to have at least two carbon atoms bonded together with a double bond to have an alkene. Now, as we're going to see later, if they have more than one double bond, then it's going to be called a diene. So just ENE means one double bond between the carbon atoms. Here's an example here. Notice the carbon atom is between the first and the second carbon atoms. The double bond is between the first and the second carbon atoms. And here it's in the middle of the molecule. And so on the naming of it, we have to say where the double bond is. And so since it's between the first and the second carbon atom, on the one on the left, and we call this 1-butene. And 2-butene means it's between the second and the third carbon atoms. Now you notice if the double bond were over here on the right instead, this would still be then 1-butene, because we start numbering from the end that the double bond is closer to. So for this particular example, you can have a 1 or a 2-butene, but you couldn't have a 3-butene. Now here are two that look pretty similar. We have a double bond between the two carbon atoms, but you notice that the chlorine atoms here are on the same side of the molecule, and the hydrogens are on the opposite side, whereas over here in the second example, the chlorines look like they're across the double bond, and so are the hydrogens. So these are two isomers that are called cis-trans isomers, and we would actually put the word or the prefix cis and trans in front of the name. So cis means on the same side, and trans means across the double bond. So we have cis-dichloroethylene and trans-dichloroethylene. And these compounds would have slightly different physical properties. Notice that the trans is much more symmetrical than the cis, and the molecules would line up much better. Now, I'm sure you've heard of trans fats. They were big in the news maybe about 10 years ago, and how most cities and I think most of the country have banned the use of trans fats in foods because trans fats are not natural substances, and they were afraid that they were going to be causing all sorts of problems. I don't know if they ever really did cause any problems, but they know the fear was out there. And companies use trans fats because they had a much longer shelf life than the regular cis fats. Cis fats are natural, trans fats are not. That might be one of the reasons why they lasted much longer. All right, alkene reactions. Here we have ethane. This is C2H6 to be ethane. Here the carbon atoms have single bonds between them. And by use of a platinum catalyst, we wind up taking two hydrogen atoms off. Here they are now by themselves, and having the carbon atoms double bond. So this is one way to make an alkene if you need to. Also, now you can do addition reactions, which means we can take the double bond, and if you recall from your bonding, a double bond is not made up of two single bonds. The double bond really has one bond that's a regular single bond, as we saw before, and the other bond in it is a little bit weaker. In fact, just calling bonds double and single really doesn't explain about the reactivity. Even though we have a double bond here, the weaker of these two bonds is where the reactive site is, because you're talking about the energy needed to break a bond. So the bond between these two carbon atoms, it might be a double bond, but of that double, one of them is what we call a pi bond, and a pi bond is weaker than the other bond, which is called a sigma bond. Now you may or may not have covered that bonding theory in General Chemistry 1. But you just want to know for now that the reactive site is where the double bond is. So that pi bond, which is weaker, will break, and then we can add a hydrogen atom to one carbon and a bromine to the other. And here are our products. Now we can also add two bromine atoms. As you see here, now each carbon atom has a bromine on it. Now what if we have a compound like this? This is, as we saw this one earlier, this would be 1-butene, and we're going to react it with HBr. So which carbon will get the hydrogen and which carbon will get the bromine? Now, if you look over here, it looks like the carbon on the end got the hydrogen, and the carbon just in got the bromine. Now, there's a rule for which carbon is going to get the bromine on it, which one will get the hydrogen. This is called Markovnikov's rule, and the C, or the carbon with more hydrogens, gets that hydrogen. And so if you look back here, this is the carbon. This had 2 hydrogens. This one only had 1. So therefore, this guy will get the hydrogen. And that's how that goes. Now, as far as naming goes, this is 1-butene. And then over here, because the bromine is attached to the second carbon atom, if you recall from a previous PowerPoint video on part 1 of organic chemistry, this would be the bromine on the second carbon. So this would be 2-bromobutane. Let's take a look at some isomers of butene, C4H8. Now here's 1-butene that we saw already today. Now here's another one. This would be cis-2-butene. Now the 2-butene says that the double bond is between the second and the third carbon atoms. And the cis would mean that the hydrogen atoms are on one side, and these 2 groups, which are really like methyl groups, will be on the other side. And one thing about the cis and trans isomers, the double bond rigidly holds these atoms in place so that they're not free to rotate around the molecule. Now here we have trans 2-butene. See, the hydrogen atoms are across the double bond like that. We could also have cyclobutane. Now in cyclobutane, we don't have any double bond, but it still has that formula C4H8, and that's why it's called an isomer of butene. Now here's one here, methylpropylene. Now you might wonder, how did I get the propylene here? Well, if I wanted to draw where my longest continuous chain is, I want that double bond between 2 carbon atoms to be part of my chain. So this is really my chain here. So I'm going 1, 2, 3, and then that methyl group is on that second carbon atom. Now you might wonder, why don't they call it 2-methyl? Well, because we only have 3 carbon atoms, that methyl group could only be on the second one. There's no other place for it to be, because if it was on the end, then it wouldn't be propylene anymore. It would be butene. So therefore, we just have to say methylpropylene, not 2-methylpropylene. Now here's another one where we have, the triangle represents cyclopropane, and now we have a methyl group attached to one of the carbons. Now you notice they're not saying 1-methyl, because in a ring there is no 1, unless we have another group attached to a different carbon atom. Then we have to number them. But right now, we just have methyl cyclopropane. Alkynes have the general formula CnH2n-2, where n is a small integer, small whole number. You have to have at least 1 triple bond in it. And here's an example. This would be 1-butyne. And we can have 2-butyne. We're going to follow the same rules for naming as we did with the alkenes. First thing you have to do is number the carbon atoms and to get the double or triple bond at the lowest number carbon atom. So we always go from the end the double or triple bond is closer to and start numbering from there. So we can have 1-butyne and 2-butyne, but not 3-butyne. Now one of the most popular or common alkynes is acetylene, which is used in welding. And we can make acetylene by adding calcium carbide, which is CaC2. Here it is here, to water, and we spontaneously get acetylene produced. And acetylene, again, I mentioned, is used in welding. It produces an awful lot of energy when you burn it. Alkyne reactions. First one we have is hydrogenation, where we can add hydrogen and part of the triple bond will break. Remember, as I mentioned earlier, a triple bond is actually 1 sigma bond and 2 pi bonds, and the pi bonds are the weaker bonds. And so you can break those 2 pi bonds and then add hydrogen atoms to the carbon atoms. So here we're just partially hydrogenating it. So we're going from ethine or acetylene to ethene or ethylene. A lot of times you hear the word hydrogenation mentioned with fats. If you start with an unsaturated fat, which would be a liquid, an oil, you can change it to a more solid state by hydrogenating it. And they call it partial hydrogenation because you're not making it completely saturated. You see this most commonly with margarines. If you look at the back of any kind of a margarine container, it'll tell you what partially hydrogenated oils are present. So here we have addition reactions where we're not adding hydrogen now, but we're adding other things besides hydrogen. So here we're reacting HBr with it. Here we're adding two Br atoms, two bromine atoms. And here we're adding more bromine atoms. So you notice we can go from the triple bond to the double and also then to the single bonds. Now, next thing we're going to look at is the alkadienes and the alkatrienes. So a diene means two double bonds, and a triene would mean three. So here's an example here. And to name this, we count the carbon atoms. So we have 1, 2, 3, 4, 5, 6 carbon atoms. So the prefix is going to be hex. We have two double bonds, so it's going to be hexadiene. So hexadiene means two double bonds with 6 carbon atoms. And the last thing to do is to say where those double bonds are. So you notice this one is right on the end, and this one is a little bit further in. So let's start numbering from this end. And I wind up with 1, 4 hexadiene. So this is the 1, 2, 3, 4, 5, 6 carbon atoms in the chain. So the first double bond is between the first and the second carbon atoms. That's why the 1. And the second double bond is between the fourth and the fifth carbon atoms, and that's why it's 4. So 1, 4 hexadiene. If you number the other way, it would be 2, 5. So we want the lowest numbers that we can for numbering the carbon atoms. Now here's another one. Why don't you take a shot at naming this one? So pause the video for a second and then come on back and see what the name would be. And this one would be 134 heptatriene. So we kind of name it backwards, remember, like we did before. Hepta means 7 carbon atoms in the chain. A triene says 3 double bonds someplace. And then we have to just number them in such a way that we get the lowest numbers. So here we have 1, 3, 4 heptatriene. That's 7 carbons with 3 double bonds. Next thing we're going to look at are a type of isomer called an optical isomer. Now earlier in this slideshow we saw cis-trans isomers. Now these are all types of what we call stereoisomers. Isomers that have a different arrangement and thus have different properties, but where the bonding and everything is the same. Everything else is the same. So an optical isomer is one that rotates the plane of polarized light. A polarized light is light where all the light waves are lined up in the same direction. Sunglasses change light that's all scattered into polarized light. Take the clear out of it. And so what happens if you have a solution of one of these optical isomers in there and you put polarized light through it, it won't go through in a straight line. You find that you can rotate the plane of it. It'll bend it to the right or to the left. So we're going to take a look at some of these. So an optical isomer, besides rotating the plane of polarized light, contains a carbon atom bonded to 4 different atoms or groups. And if that's the case, then it's going to be called chiral. Now, if it isn't like that, then it's going to be called achiral. So we're going to take a look at some of those. Now let's take a look first of all at the achiral molecules here. So the one that we have a carbon in the middle, and then we have 2 hydrogens over here, a bromine and a chlorine. Now if you put this in front of a mirror, it looks exactly the same. In fact, you can take one and put it right over the other, and everything is lined up just as it was. So these guys are achiral, whereas these over here don't line up like that. And so here we have, you notice we have a carbon in the middle bonded to 4 different atoms. So if we replace one of the hydrogens with a fluorine, Now, if you look at this in the mirror, you notice that the fluorine and hydrogen look like they change places. So they're mirror images of each other. And if you take one of these molecules and put it right on top of the other, you see that the fluorines and the hydrogens are not in the same place. And that's called chiral. So a chiral molecule is one that's where it's a mirror image of itself. Now, mirror images are different. You have, for instance, you have handedness yourself. Your right hand, if you put your right hand on top of your left hand, you notice that not everything lines up right. The thumbs are on opposite sides, the little fingers are on opposite sides. So your hands are chiral. Here are some other objects that are chiral. You have a right shoe and a left shoe. We have a left mitt and a right mitt. We have right-handed and left-handed scissors. Now, if you're right-handed, you don't even notice that because almost all the scissors you see out there are made for you. And people that are left-handed either have to learn how to use their right hand with scissors, or they have to buy left-handed scissors. Now, here are some objects that are achiral. A glass, if looked in the mirror, looks exactly the same. Plates and a tennis racket look exactly the same. But if you put any one of these three on the left in a mirror, you'll be looking at the mirror image of it. So a right shoe looks like the left shoe in the mirror. A left mitt will look like the right mitt in the mirror. Okay. Here are some more to look at. Now oops, I'll go back on this. Now there's a term here, enantiomers. And an enantiomer is just a type of chiral molecule. You may or may not see that term in the textbook. So let's take a look here. Here we have a molecule. There's a carbon atom in the middle, and you notice 4 different atoms. This is similar to the previous slide. And here's the mirror. Now you notice that these two guys then are mirror images of each other. So the molecule is chiral. So enantiomers of a chiral molecule are mirror images. So each one of these is an enantiomer. Now for B, if you try to line them up, you see what happens. They don't line up right. The chlorine and the bromine are on opposite sides. So the enantiomers of a chiral molecule cannot be superimposed on each other. And that's what I was talking about when I said putting your right hand over your left hand. Now you see this is very important in living organisms. There are molecules that are handed. They say they have the property of handedness, left hand versus right hand. And we'll take a look at another one now. We have a glyceraldehyde at the top and we have glucose in the bottom. Now if we look up here, we have a carbon atom in the middle, and for instance this carbon atom is bonded to this CHO group, OH group, a hydrogen, and a CH2OH group. See, these are 4 different atoms or groups bonded to that carbon atom. So therefore this carbon atom here can be chiral. The whole molecule will be chiral. So if we look over here, what's the difference between these two? Well, the OH group is on the right over here, and it's on the left over here. So this one we call the left-handed molecule, or L-glyceraldehyde. And this one would be called D for right-handed molecule. So it's on the right, the OH is on the right-hand side. So L and D are letters that are used to designate the different optical isomers. L for left, and D, I know you might say, why not R for right? Well, they don't use R, they use D for, D means dextro, which is the Latin word for right. Sometimes instead of seeing L, you see S, which is short for the Latin word for left, which is sinister. Now let's look at the glucose ones, because this has some importance to us. There's L-glucose and there's D-glucose, dextro and levo, and the 2 different isomers. And you see, this is the carbon atom that's chiral right here. So for this guy, see how the OH is on the right? Here it's on the left. Now we can only digest D-glucose. And it seems like at one point in time, there must have been L-glucose around as well as D-glucose. But this is the only type of glucose that we can digest. If you were fed L-glucose, you wouldn't be able to digest it and you would wind up starving. Okay, aromatic hydrocarbons. Now, aromatic hydrocarbons contain a benzene ring. And this is what benzene looks like. If you notice, we have 1, 2, 3 double bonds. And same thing over here, but it looks like the double bonds are rotating within the molecule. That's the way some people picture this. that the double and the single bonds between the carbon atoms rotate around each other. Other people say, well, you know, if they did do that, the bonding would be a little bit different and some of these bonds would be weaker than others. It appears that the bonds have the same strength, so it might just be that we can't draw these things correctly using Lewis structures. So maybe the bonding is something between a single and a double bond. Now, this is another way to represent it. And this is the way you most commonly see benzene drawn. You see benzene with this hexagon with a circle in the middle. So that's benzene. If you didn't have that circle in the middle, that would be cyclohexane. So aromatic hydrocarbons are going to have that benzene ring. Now, they call it aromatic because they have, you know, the aroma isn't too bad, or the odor from it. Now, here are some different types of aromatic hydrocarbons. We have ethylbenzene, so we have an ethyl group attached to the benzene molecule. We can have chlorobenzene, here's a chlorine atom attached. We can have aminobenzene, here's the amine group attached to it. We can have nitrobenzene. Now notice I didn't bother saying 1 or 2 or 3, and that's because there's only one of these groups attached. But if you have more than one of these groups attached, you have to start saying where they are, and we're going to be numbering the atoms. So we'd number it like that. Now, we're just going to be numbering 1 through 6. Depending on where that group is, we're going to call whatever that group is at the number 1 carbon. So how would you name this one? Well, that would be 1,2-dibromobenzene. And what about this one here? Well, here, if this is the number 1 carbon, then this would be the number 3 carbon. So this would be 1,3-dibromobenzene. So if you just keep in mind that your goal is always to describe a molecule so that somebody someplace else could draw it out and know what it looks like. Now we have, from the previous slide, we have 1,2-dibromobenzene and 1,3-dibromobenzene, and we could have 1,4-dibromobenzene. Could we have 1,5-dibromobenzene? And that would be no, because 1,5, which you think would be right here, would be the same as 1,3. So we can go 1,3, but we can't go 1,4 or 1,5. I'm sorry, I did that wrong, I think. So we can have 1,2, 1,3, 1,4. So here are those names. Now, because these positions are very common, the 1,2, the 1,3, and 1,4, they have other names. The 1,2 position is called ortho. So this would also be called ortho-dibromobenzene. The 1,3 position is called meta, and the 1,4 position is called para. Para-dichlorobenzene was actually mothballs, which was a very popular, actually poison. I didn't want to call it a poison, but people would put mothballs in with wool clothing that they were going to store over the winter. And the mothballs would sublime, they would just vaporize and fill up the container with this gas. And the gas would kill the moth larvae. You don't even see these larvae because it's so tiny, but they're the things that eat the wool and put the holes in the clothing. And something that isn't even used anymore because people are finally realized that breathing in that vapor, if it's not good for moths, it's probably not good for us either. And now here are 2 other aromatic compounds with methyl groups. We have methylbenzene and dimethylbenzene. Now we could say 1,2, if we wanted to, 1,2-dimethylbenzene. But for these 2, they have their own particular names because they're very common. The first one is called toluene. The second one is called xylene. So methylbenzene is xylene, and 1,2-dimethylbenzene is, I'm sorry, I think I said that wrong. Methylbenzene is toluene, and 1,2-dimethylbenzene is xylene. Well, what would this structure be called? Well, let's see. There are 3 nitro groups on it. We want to probably number them because they can be in different places. And then we have that methyl group. So we could call it 2,4,6 trinitro-methylbenzene. So we're saying, okay, this is the number 1, so we're just going to call that methyl. Now you might wonder, why don't we say where it is? Well, because no matter where it is in here, it's in the same place. Because it's between 2 nitro groups, no matter where we put it. So that's why they didn't bother saying the 1. So that's 1, that's 2, that's 4, and that's 6. So 2,4,6 trinitromethylbenzene. The other way to name it is to look at the structure as being this. So if I said that's my basic structure, you notice it matches up with this guy here. So I could call it 2,4,6 trinitrotoluene. Now, this is a very common compound, and they know it by it's only 3 letters. This is called TNT. Is my explosion. So TNT is actually this compound here. Some people think it's dynamite, but it isn't. It's trinitrotoluene. Okay, let's take a look at some aromatic compound reactions. We can have a substitution reaction. So here we're reacting, here's our benzene, we're reacting with bromine. We need a catalyst using an iron 3 bromide catalyst. And what we've done is we've substituted for one of the hydrogens that's bonded to the carbon here. Now you might wonder, I thought we had like alternating double and single bonds in the molecule. Could we just not add atoms to these carbon atoms? You know, break the double bond and add an atom in it? And no, it seems like aromatic compounds, they resist addition reactions. And this is another bit of evidence telling us that maybe the bonding isn't single and double, but it's something else that's pretty strong. Now here's another example here. We have here's our benzene, and this is ethyl chloride, or we could call it chloroethylene. Here's another, we have aluminum chloride catalyst, and now we have the ethylene group attached to the benzene ring. This is called ethylbenzene. Just to go for the top here about the naming, phenol is the name of the alkyl group when it comes from a benzene ring. So if you pop off that hydrogen, then they call it phenol. So sometimes you see that in there. They also can call it benzyl. So, again, in chemistry, there's a lot of naming that you have to get down.